Musical instruments rely on standing waves to make sound, like we see on the guitar here. But why are there standing waves? Remember that standing waves require a wave moving to the right and another wave moving to the left to produce the standing wave. Why are there, on a guitar string, waves moving in both directions? The answer is from reflections. You see, there are waves traveling to the right, which reflect off the boundary, the edge of the string, and that produces a right moving wave and a left moving wave. In this animation, what we see is, first of all, the top string is clamped down at this black point here. And you see that there's a reflection produced, which is inverted. An inverted reflection occurs. The reflection has to be inverted so that the reflection cancels out the incoming wave at this point. Basically, the clamped portion pulls down on the incoming string and produces a wave which is inverted or upside down compared to the pulse that's coming in. On the second string, the string is not clamped, but is free to slide up or down on the metal rod. And when that happens, the pulse is not inverted, but the pulse reflects back upright with the same orientation as the incoming pulse. In fact, notice that this end of the string actually stays flat as the reflection occurs. That'll be important when we talk about the standing waves that are produced. So it's possible to create different boundary conditions on the string and get different kinds of reflections. That'll give you, as we'll see, different kinds of standing waves which occur. So now let's work out the details. Let's now look at a string which is fixed at both ends. Like a guitar string is basically the string is unable to move at either end of it. A couple things we have to remember first. Number one, that the speed, let's say the frequency of a given wave is the speed of the wave divided by the wavelength. That's true for any, for any type of wave. Also remember that for waves on a string, we can predict the speed of the waves if we know the tension and the mass of the string. So that's only true for transverse waves on a string. If you're talking about sound waves, you have to plug in the speed of sound. Okay, so if we have a string which is fixed at both ends, let's look at what kind of standing waves we could have on there. It has to be a node at both ends. Node, remember, means no displacement of the standing wave. In other words, like what we see here. The standing wave here is a node at both ends, and that's what we need if it's clamped at both ends, like on a guitar. So, what kind of standing waves could we have here? Let's ask first, what's the longest possible wave which can have nodes at both ends? Well, it would look like this. And it would oscillate up and down. So we usually draw it like this. It looks like a loop. It's really just showing you that there's half of a wavelength oscillating up and down on this portion of the string. That's the longest possible standing wave that you could have. Anything longer than that, it wouldn't have a node in the right place. Okay, so let's look at what this wavelength is. I'm going to label this with a number 1 because it's the first. And so we'll say lambda 1. How big is that wavelength? Notice it's not equal to the length of the string. In fact, the wavelength would be twice the length of the string. If I were to draw the full wavelength, it would extend out to 2L. That shouldn't alarm us. Yeah, it's fine for only half of a wavelength to fit on the standing wave. Okay, so lambda 1 is equal to 2L. Then what about the frequency? F1. What frequency would this wave be? Well, it would be the speed divided by the wavelength. That's V over 2L. Remember, if it's a string, we know the speed if we know the tension and the mass. Okay, So that would predict what we call the fundamental frequency of the guitar string. Like an E string, if you pluck the E string, this is the dominant mode of vibration which is activated when you pluck the string. Just like when you strike a bell has a certain resonant frequency. The guitar string has this fundamental resonant frequency. However, a bell only has one. A string has an infinite series of harmonics or resonances, as we'll see. Let's look at the next one. It's the same string, fixed at both ends, node and a node. Can I get a somewhat shorter wave to fit? Sure. I could get a wave which has a node right in the middle, and it would look like this. That's a freeze frame version of it. Looking at it like in that strobe video that we saw, it would look like this, vibrating up and down. So in this case, the wavelength is exactly equal to the length of the string. That's half the wavelength, therefore double the frequency. Look at the equation. If you halve the wavelength, you double the frequency. This means this is number 2. F2 has twice the frequency of the fundamental. That's another possible resonance that you can get on a guitar string. Guitar players know this. You can put your finger at the center of the guitar string and pluck it, and it produces what you call a harmonic. And that's just one of the other resonances of a guitar string. Let's draw one more. Can I get an even shorter wavelength or higher frequency to resonate on the string? Sure, I just have to fit 2 more nodes on here. I mean, fit 1 more node, I should say, compared to the previous one. Like so. Still has nodes at both ends, but now it has 2 additional nodes in between. How long is the wavelength here? Well, here the wavelength is from here to there. The wavelength in this case is therefore 2/3 of the length of the string. Or in other words, it's 1/3. If you compare it to lambda 1, it's 1/3 of lambda 1. So it's 1/3 of that wavelength, which means the frequency is 3 times. This is F3. It's 3 times F1. So we put down here the first 3 resonances of a guitar string. These are what we call the harmonics or the harmonic series. Unlike ringing a bell or vibrating a mass on a spring, those only have 1 resonance. A guitar string has an infinite series of resonances. They're called the harmonics. Now, what if we change the boundary? In other words, what if we change this end of the string so that it's free to slide at one end? So here's a different possible boundary condition. I'll draw it like with a circle, indicating it can slide up or down at that position. Well, remember, this has to be a node. This end actually stays flat, even as waves move along on this string. The end that's free to slide has to stay flat. The reason is this rod can only pull horizontally on the string. The rod is frictionless, so it can only pull horizontally on the string, and therefore the string can only have a horizontal orientation at that free end. So that means it has to be an antinode at this position. So what kind of wave can you get then? What kind of standing wave can you have there? Well, it has to be a node here, antinode there. The longest possible wave will then look like this. And it oscillates up and down, with that being an antinode. It means we sketch it like this. And it goes up and down in this position. What's the wavelength of that? This, you should be able to tell, that is only a quarter of a wavelength. This over here is half of a wavelength in this picture on the left. That's half a wavelength. This is a quarter of a wavelength. In other words, the wavelength here is 4 times the length of the string. So if you arrange the string to vibrate with an antinode at that side, it will have twice the wavelength compared to the node-node situation. Twice the wavelength means it'll have half the frequency. In other words, F1 in this case will be V over 4L. It will resonate at a lower pitch just by changing the boundary condition. And I'll show you some examples of that soon. Let's first work out the other resonances. Still has to be a node at this end and an antinode at the other end. But now I can fit another node inside of it. So like that. This wavelength, how long is this wavelength? Well, what you see right here is 3/4 of a wavelength. 1/4, 2/4, 3/4 of a wavelength are present. In other words, in this case, the wavelength is 4/3 L. And I shouldn't have called it lambda 1. It's not lambda 1. The wavelength in this case is 4/3 L. So what about the frequency? The frequency in this case, notice it's 1/3 of the original wavelength. It means it'll be 3 times the original frequency, F1. Notice how changing the boundary not only made the pitch lower for the lowest frequency compared to this one, but it also means you skip some of the resonances in between. You go from F1, there is no F2, you skip right to F3. Totally changes the pattern of the resonances. If you fix it at both ends, you hit F1, you hit F2, and F3, and so on. On this one, you only hit the odds, F1, F3. The next one will be 5. I'll sketch it. It will look like this. Now it has 2 half wavelengths and an extra quarter wavelength, like so. The wavelength here, so I should call this one lambda 3. This one is going to be lambda 5 because there are 5 quarter wavelengths. 1, 2, 3, 4, 5 quarter wavelengths. The wavelength in this case is 4/5 of the length of the string. And this one's F5 then. F5 is 5 times the lowest or the fundamental frequency. Okay. One more option is it's possible to arrange antinodes at both ends. What's the fundamental look like now? Well, both ends have to have antinodes. It has to vibrate up and down. That means there's got to be a node right in the middle. And the vibration looks like this. The ends vibrate out of step with each other, up and down with the antinodes at either end. And if we draw what it looks like, it moves like this with antinodes and antinodes. What's the wavelength in this case? Well, the wavelength, this is exactly half of a wavelength that's on the string. In other words, the wavelength is 2L. The frequency then is just V over 2L, just like it was for the node-node situation. Let's draw out the next one. Free at both ends, but now I'll have an extra node in the middle, like this. This is now a full wavelength, lambda. See a typo here, this should be lambda 2. Lambda 2 is just equal to L in this case. That means F, we have F2, which is equal to 2F1. In fact, it's exactly the same pattern as the node-node situation. Let's summarize all the results here. If it's a node at both ends, we saw that the nth harmonic is equal to n times v over 2L. And you hit every integer value, 1, 2, 3, and so on. 0 is not an option. That would be like no wave at all, no frequency. Doesn't make sense. Then if it's a node-antinode situation, you get an infinite series of harmonics. In this case, they come out to be n times v over 4L. Remember, the fundamental one in this case had a wavelength that was 4 times the length of the string. So the fundamental one here is half the frequency as the node-node situation. And you have to skip the evens. So you go 1, 3, 5. It's only odds. And then the third case was if it was antinode. In that case, it's exactly the same as in the node-node situation. It looks different, the waves look different, but same frequencies. So now let's do some examples. Actually, I'll show you some illustrations, some simulations of these standing waves, and then we'll do some examples. Those are some harmonics of a guitar string. First, you heard the fundamental. That's just what you hear when you pluck the string. Then, by touching at the halfway point of the string, I can produce the first overtone or the second harmonic. Notice that the entire length of the string is vibrating, well, except the node, but it's not that I'm stopping the string at the halfway point, so that only half of it vibrates. No, the entire string is vibrating. It's just that I force there to be a node there, so it produces the harmonic. Then, by touching the string a third of the way, that produces n equals 3 harmonic. And then one more was at the quarter length of the string that produced n equals 4. Again, the entire length of the string is vibrating when the harmonics are produced. That's very different, and it produces a very clean bell-like sound because it's a sine wave. It's a sinusoidal wave. Very clean, pure frequency is produced. The whole length of the string is vibrating, except the node points. That's very different from the way you normally fret a guitar or a violin or something like that. Normally, when you fret the strings, you're actually changing the length which is vibrating. So if you shorten the length which vibrates, smaller length, smaller wavelength, higher frequency. So you move up the fretboard, that increases the pitch of the fundamental frequency. That's the normal way you play it. The harmonics are a special way to just touch those node points to produce the harmonics. In this problem, we have an oscillator on the left side. They call it a vibrating blade. It's vibrating at some frequency such that it sets the string into its second harmonic. There's a certain weight hanging from the string that provides the tension. Now, in the second picture, the wind blows, provides an extra force that pushes the mass to the right. That will, as we'll see, increase the tension. And when the tension in a string increases, the waves move faster. Think of tuning a piano or a guitar string. You crank up the tension, the waves move faster, and that boosts the frequency. Now, in this case, the frequency is being held fixed. there's something driving the string of a fixed frequency. So when you increase the tension, it's going to not be able to change the frequency in this case. Instead, what's happening is the wave speed is larger. The wave speed is larger, and it's just that the wavelength for that given frequency is now longer. In other words, what I'm saying here is that the wavelength, which is v over f is staying the same, but the tension will grow. So this is 1 over f times the square root of tension over mu. What we know is this has a wavelength, let's call it lambda naught, the original wavelength. It's just equal to the length of the string. But in the second picture, with the speed higher but the frequency the same, now the wavelength has doubled. Now the wavelength would be twice the length of the string. Twice the original wavelength. Okay, so how can we achieve that? If I want to double the wavelength, I must double the speed of the waves. And you can do that by increasing the tension. But it's just that you have to quadruple the tension in order to double the speed. You see, it depends on square root of the tension. So we need the new tension to be equal to 4 times the original tension. 4 times the weight of the block. Okay, so now it's a mechanics problem, force diagram type problem. Let's draw the force diagram for the block in the second situation. We've got 3 forces that act on the block. There's the weight of the block, which is just equal to the original tension. There's the wind pushing to the right, F. And those 2 forces are being balanced by the new tension in the string. That's T, which is equal to 4 times the original tension. But let's draw a force diagram, and let's draw the vector diagram and see what we have. The block is in equilibrium in this picture. It's not moving anywhere. It's just being held in place by the 3 forces. So we've got a nice right triangle. I've got there's T naught vertically. We've got F to the right. And we've got the new tension, T, along the hypotenuse. So I have T squared is equal to F squared plus T naught squared. Remember, our job is to figure out the value of the force from the wind. So this means I've got F squared, or let's say F. F is going to be equal to the square root of T squared minus T naught squared. But we already knew, based upon the change in the wavelength, that T has to be 4 times T naught. That gives me 16 T naught squared, or subtracting, I get 15, and I get the square root of 15 T naught. So there we go. That's how strong the wind must be to put it back into the first harmonic from the second harmonic. In this question, we have 4 grams of steel to use, and I want to know how long and thin can it be such that it'll withstand a pull from either end of 900 newtons without breaking. So there's a certain maximum force applied to both ends, putting under tension. And I want to know how long can it be, how skinny can it be. The idea here is the skinniness is determined by the breaking stress of the steel. If you just take like a chunk of the steel, you could pull on it super hard from both ends and it won't break. But as you draw it out thinner and thinner and thinner, eventually it would snap under 900 newtons. The breaking stress measures how many newtons per square meter, how much force per area the molecules in the steel can withhold before they snap. So we'd first figure out how what area it's going to be. And then knowing that it's 4 grams will determine how long that string is. Okay, so the idea is I'm going to set F max equal to the breaking stress, which is written with the letter Y, times the area. This is the cross-sectional area. It's a circular area, like a disk, of the string. So F max is 900, Y is given, and so therefore we solve for A. I get a value for A, which is 1.29 times 10 to the minus 6 square meters, which then you set equal to pi r squared to find the radius. Next, we want to know what the length must be. Now I know how thin it is. I need to know the length. Well, I'm given that it's 4 grams, so I can solve for the length because the length, this thing is just a cylinder. So the length of it is just its volume divided by its area. And the volume I know because the volume is the mass, 4 grams, divided by the density of the steel, and it's that divided by the area. Gives me a length of 0.399 meters, 339 meters. Okay. Next up, what's the highest fundamental frequency that this string could have? So this is just plugging into our equation for the harmonics of a string, which are n times v over 2l. This is a string fixed at both ends. I'm assuming it didn't say that, but it's a guitar string. So I know a guitar string has fixed points at both ends of it. The fundamental is number 1. So we're looking at F1. N equals 1. The speed is 1 over 2L. The speed of a wave on a string is the square root of the tension, which is F max. I'm assuming 900 newtons of tension, divided by mu. Now, it's easiest in this problem. I'm not given mu directly. I'm given the length of the string. Well, I found the length, and I know the mass of the string. So it saves a little bit of time to simplify this. Mu is 4 grams divided by L. So if I write that in, L goes up in the numerator, and there's a cancellation that occurs, or a simplification that occurs, with the L out in front. And so I get 1/2, and then I get the square root of F max, and then I get in the denominator m times L. That's the square root of L canceling the, simplifying with the factor of L in front. That means I plug in here and I get 376 hertz.
Okay, let's see if we can hear it this time. Where's the sound coming from? Where? Only the ends. Only the ends. Amazing.
That was a demonstration called the singing rod. And what you saw there was the demonstrator holding the rod at the center, putting rosin on his fingertips, and stroking it to set it into a longitudinal vibration. It's not transverse waves in a rod. Transverse waves in a rod, that's what you get if you just like knock the rod on the ground. It'll vibrate in a transverse fashion. This is longitudinal in and out vibrations along the length of the rod. We, in this question, want to figure out why the ends are antinodes, what the fundamental frequency is, and look at some of the higher harmonics. So the reason it's antinodes at both ends is that it's an analogy with a string which is free at both ends. A guitar string's fixed at both ends, but in this situation, the vibrations are free at both ends of the rod. So the fundamental frequency would appear like this. Now, this is for a string where we're looking at the vibrations up and down at the ends of the string. For our rod, a better way to draw it is, here's the cylinder of the rod. The ends of it vibrate in and out. It's a longitudinal wave that we're talking about. The center doesn't move at all. It's a node at the middle. So it's just like a string with antinodes at both ends and a node in the center. The demonstrator held it at the center, stroked the ends with rosin on his fingertips, and that set it into the fundamental. We want to predict what the frequency would be. In this case, it's steel, although his might have been aluminum. But anyway, a steel rod. We want to predict what the frequency would be. This is F1. Now, remember that for free at both ends, the equation is the same as with fixed at both ends. For instance, to find the first frequency, I would take V over lambda. But the wavelength here is just 2L. It's exactly the same as a string fixed at both ends. Of course, the pattern looks different, but the equations for the frequencies are the same. Okay, so we predict F1. We have to take the speed of sound and in steel, which is almost 6,000 meters per second, divide it by twice the length of the rod, which in this case 2L would give me 3 meters. So it gives a roughly 2,000 hertz, which is in the ballpark of what was observed in the video. It's not exactly 2,000. It comes out to be 1930 hertz. A fairly high-pitched sound like we heard in the video. Then we want to predict the next possible standing wave. So what would the next one look like? Well, as you go from one harmonic to the next, you always just fit one more node in the pattern. So it has to have antinodes at both ends. But now there's an extra node in between. An extra half wavelength is present. For a string, it would look like that. For our rod, it would look like this. The ends are always antinodes. But now there's an extra antinode in the middle. So the middle oscillates back and forth with high amplitude, and there are nodes over here and over here. Okay, so this is just F2. It's F2. F2 is just twice F1, and it's 3860 hertz. If we were in the classroom, I would show you this with a steel rod. To produce the fundamental, I hold it at the center. To produce the first overtone, or the second harmonic, I would have to hold it closer to the end. Where exactly would I hold it at in order to produce the second one? Well, let's look carefully here. Here's a quarter wavelength. Here's another quarter, quarter, quarter. So now it's split into 4 quarters. I would have to hold it at 1/4 of the length, 1/4 L, and rub the ends with rosin on my fingertips, and I'd be able to produce a double frequency harmonic. Stringed instruments like guitars, pianos, they are strings fixed at both ends, and we saw the harmonics that are produced. When we saw the singing rod, which is a sort of a musical instrument, it's free at both ends. We saw the harmonics there. Wind instruments like flutes and clarinets, for example, they also they rely on standing waves to produce their sound. They fall into 2 categories. They are either open pipe resonators, where both ends of a tube are open to the air, to the outside air. For example, a flute is essentially open at both ends. It's open on one side, and it has a mouthpiece at the other end, which has an opening. A clarinet, on the other hand, is what we call a stopped pipe resonator. It doesn't mean that both ends are stopped off. It just means that one side is stopped. So the clarinet, of course, it does have a very small opening with a reed on it, but it's effectively blocked off there, and the reed actually just kind of acts like a vibrator, an oscillator, which sets the air column into motion. That's a stopped pipe. Um, if you sing in the shower, the walls stop the air at all sides. But typical musical instruments fall under these two categories. So if it's open at both ends, that means that both ends of the air column are going to be antinodes. It means the air will move in and out with maximum amplitude at those ends. And that's how a flute operates. And we know that this is like the singing rod or the string free at both ends. And we know the rule there is that the harmonics are given by n over 2L times V. In this case, this is not waves on a string where you plug in the tension to find the speed. You plug in the speed of sound in air. If it's a stopped pipe, we saw that changes the patterns. A stopped pipe has to have a node at this end. The air doesn't really move there. It's trapped against the wall, but you got an antinode at this side. And so we saw the pattern that's produced for the harmonics. In this case, it's n over 4L times V. And notice carefully that in this case, n is odd integers. In the open pipe case, all integers are allowed. Okay, so we're told that we have a certain organ pipe. It has two successive harmonics with these two frequencies. And from that, we're supposed to figure out whether it's open or stopped. The key thing is, if it's a stopped pipe, when you go from one harmonic to the next, n increases by 2. But open pipe, going from one harmonic to the next, it just jumps by 1. The integer increases like from 2 to 3. Stopped pipe, it's only odds, so you would jump by like 5 to 7, for example. So to figure out which kind it is, I'll take a ratio of the two harmonics. What I'll do is I'll take 1372 divided by 1764, and I'd see what that ratio is. It comes out to be 5 over 7. 7 over 9. Seven over 9. Of course, it's also 14 over 18, but those wouldn't be two successive harmonics. Okay, so since they're successive, I know that 1372 is the seventh harmonic of the stopped pipe. It's a stopped pipe resonator. It's a seventh harmonic and the ninth harmonic. And what is the length of the pipe? Well, I could take 7, for example. F7 is 7 over 4L times the speed of sound. I would plug in the speed of sound, 343 meters per second, and plug in the frequency and solve for L. I get a length which comes out to be about 0.4 meters, 0.4375 meters. So it's important to be able to visualize what the harmonics look like in the different conditions so you can draw them out correctly and keep track of the difference, whether it's open or stopped. There are only two equations you work with, the n over 2L equation or the n over 4L with the odd numbers. Just got to know which is which, depending on the circumstances. Guitars are not just vibrating strings. The air inside the body of the guitar also resonates. Some guitars are resonator guitars like this called a dobro, and it has a metal resonating part of the body of the guitar. It changes the sound, increases the resonance of the sound. As an example of this, we're supposed to imagine designing a new musical instrument. It's a metal tube of length L and diameter L over 10. So here's the tube. The length of it is L. The diameter is L over 10. We've stretched a string across the open end of the tube. So here's the string. Sort of a crude model of a resonator guitar. To produce the musical effect you're looking for, you want the frequency of the third harmonic on the string to be the same as the fundamental for the air column in the tube. Okay, let's put that in equation form, and we want to find what must be the tension of the string to produce that effect. Okay, so we want the third harmonic of the string to match the fundamental of the tube. Okay, so that means we want 3 times the fundamental for the string. Let me call that F1. Remember, the third harmonic is just 3 times the frequency of the fundamental. So I want 3 times F1 to be equal to the fundamental frequency for the sound waves in the tube, and I'll call that Fs. Okay. So I'd like to figure out what the tension must be to make that happen. So I need to plug in F1 in terms of the tension. Okay. So let's see how it goes. This is 3 times F1. This is in the string. So this is 3 times, this is 3 divided by 2L. The length of the string, however, is L over 10. The string isn't L, that's the length of the tube. The string has length L over 10. And it's that times the speed of the waves in the string, which is the square root of the tension F divided by mu. And that must be equal to the fundamental frequency in the tube, which is 1 over 4L multiplied by the speed of sound, Vs. So from this, I can solve for F. The point is I want to solve for F. Basically square both sides and solve for that tension. It comes out to be mu times the speed of sound squared divided by a factor of 3600. And that's just algebra solving for the tension. Okay. Question B, what happens to the sound produced by the instrument if you double the tension from what we just calculated? Does that bump you up to the next resonance? No, it doesn't, because doubling the tension does not double the frequency. Notice the tension's under a square root. You would have to quadruple the tension in order to double the frequency. Okay, so the answer is, what happens to the sound? You lose the resonance. The sound is not amplified by the sound waves in the tube anymore. Okay, then question C. For the tension calculated in part A, what other harmonics are in resonance with standing waves in the air column? Okay, so we're looking for all the different harmonics which will resonate with the air in the tube. In this case, it was the third harmonic of the string matched the fundamental of the air column. But in general, I could have the nth harmonic of the string match the, let's say, the mth harmonic of the fundamental in the tube. Crucial to remember here that since it's a string, n can be 1, 2, 3, and so on, any integer, any non-zero integer. M, however, Since it's an air column that's closed at one end, this end is stopped off. It's a stopped pipe resonator. Then M can only be odd integers, 1, 3, 5, etc. So we can look at all the different M values for the air column and see what the corresponding values of N are going to be. Okay, so let's see what we have. Well, we've got N is equal to M, odd integers, multiplied by the fundamental in the tube, divided by the fundamental of the string. But remember, the fundamental in the air column divided by the fundamental of the string is just equal to 3. So this is equal to 3m. Which means that the resonances are the harmonics of the string, which resonate with the tube, are the n values, which are 3 times the odd integers. In other words, we can make a list of all the different resonances. For each m value, I'll have a different possible n value, which resonates. So I'll have a whole list of them here. I can take m equals 1 and n equals 3. We already know about that one. That was how the instrument was designed, so that the fundamental of the air column matched the third harmonic for the string. But there are more. I can plug in m equals 3 and I get n equals 9. Next, I could plug in m equals 5 and get n equals 15. And these are all the different resonances so that the string will resonate with the air column. Here we have 2 different wires that are welded together end to end. One wire is thin, the other one is a fatter wire. We don't know how long they are. I do know, however, that the tension is uniform throughout it. It's pulled at both ends with a force of 4.6 newtons. So there's a uniform tension all throughout it. Waves are being produced. The combinations vibrated in such a way that 2 antinodes are present, with a node between them being right at the weld. In other words, if we could see the standing wave pattern, it would look like this and this. Crucial to remember how this is being produced. The thing's being vibrated in some way, so maybe the left end is being oscillated to produce the waves that make the standing wave. Now remember that when waves go from one medium into another, which is what's happening here, the frequency of the waves does not change. The speed that the waves travel at changes, the wavelength is different, but the frequency is maintained. So F equals F, same frequency on both sides. Okay? What's actually happening here is waves travel to the right, they reflect off the boundary between the two. There's a portion of the waves reflected back, that's producing the standing wave in here. And then a similar thing happens on the right side where waves are bouncing back and forth on the thicker side of the wire as well. Okay, so first job is to figure out what is the frequency of vibration. Remember, it's the same on both sides. So I can use the side where I know the length and the mass density to figure it out. So what I know is that F, it's a string with nodes at both ends. Let me call them like L1 and 2, or wire number 1 and 2. So F1 is equal to F2, called F. F is equal to 1 over 2L. This is the first harmonic, right, with a node at both ends of it. So it's n equals 1 over 2L times V. V is the square root of the tension divided by the mass density of wire number 1, which I can figure it out because I know it's I'm given its mass density, and I know the length. Okay, so that frequency comes out to be 59.9 hertz. And it's the same on both sides. Given that, I can figure out what must be the length of the thick wire. Okay, so first of all, what I know is the diameter of the thick one is actually twice that of the other. That means the value of mu is 4 times as big. Let's make sure we understand why. Mu is the mass density. It's the mass of a wire divided by its length. But I need to think in terms of diameter and area. Mass of the wire would be its density multiplied by its volume. That's the area of it, cross-sectional area multiplied by the length. You divide that by the length to get the mass density. So mu can also be written as volume density multiplied by area. Therefore, if you double the diameter, you quadruple the area, and that means that mu2, the implication here is that mu2 is actually 4 times as big as mu1. What does that mean in terms of the speed of the waves and the wavelength? Well, if you quadruple the value of mu, that would cut the speed of the waves in half. So this means that v2 is 1/2 v1, because the square root of mu determines the speed of the waves. So v2 is half of v1. That lets me figure out the length, because I know that the frequency is the same on both. The frequency is 1 over 2L2 times V2, and I know that V2 is half V1, so this comes out to be 1 over 4 L2 times V1. Now, it's the same frequency on both, so this is also equal to 1 over 2L1 times V1, because F1 is equal to F2. This lets me solve for L1. It tells me, by setting up this way, I can just get a ratio to find that L2, comparing this expression and this one, I can find that L2 must be just exactly half L1, which is 20 centimeters.